Hi, Assalamualaikum and a very good morning. So now we're going to do chapter 6, chemical equilibrium. And now we're going to focus on the subtopic of 6.2 equilibrium constant, part 4 of the video. So in this video, we're going to learn about the definition as well as the determination for the degree of dissociation alpha. And next, we're going to deduce the expression for the reaction quotient and predict the direction of net reaction by comparing the values of Q, which is our reaction quotient, with the equilibrium constant. For the learning outcome of D, we're going to look about that in part 3, which is in the previous video. So for now, let us start with part 4 of the video first. So the degree of dissociation. The degree dissociation is basically a chemical reaction whereby a molecule is broken down into a smaller molecule, atoms or ions. The fraction or the percentage of the molecule that dissociate is called the degree of the dissociation, known as alpha. And if the dissociation occurs completely, then we're going to get our alpha to be 1 or equal to the 100%. And if the dissociation is incomplete, tidak sempurna, then the value of alpha can be calculated as follows, in which alpha is equal to the change in concentration divided by the initial concentration. Or you can also find the percentage of dissociation by multiplying with 100%. And the concentration here, you can also change it with the number of mole, change in the number of mole with the initial number of mole. And you will get the same ratio or the same percentage between concentration with the number of mole, because concentration is directly proportional to the number of mole. Alright, so now let us learn on how we can apply the degree of dissociation in the question. So for example, number 1, the concentration of H plus ion measured is 8.9 times 10 to the power of negative 3 molar when 0.5 molar methanoic acid dissociates. What is the degree of the dissociation of the methanoic acid compound? So the degree of dissociation here refers to alpha. And then the concentration of H plus ion, 8.9 times 10 to the power of negative 3 molar, it refers to the change, or known as the X, because when the acid dissociate, it's gonna produce a chemical equation to be something like this. So the methanoic acid will be in equilibrium with its hydrogen plus aqueous ion, as well as the methanoate ion, which is in aqueous. So they are in equilibrium between one another. So the methanoic acid will dissociate in order to form H plus aqueous ion, and this gives the value of X, which is 8.9 times 10 to the power of negative 3 molar. And because of this reason, we're going to do the ice table. So the initial concentration of HCOOH aqueous is 0.5 molar. And then at initial stage, we doesn't have any concentration of the H plus as well as the methanoate ion. So we're going to put at 0 and 0 here. And as time goes by, the concentration of the HCOOH going to be reduced by X, which is 8.9 times 10 to the power of negative 3. And then for the concentration of H plus, it's going to increase by 8.9 times 10 to the power of negative 3. Similarly goes to the methanoate ion. And at equilibrium, 0.5 plus negative 8.9 times 10 to the power of negative 3, we're going to get the concentration at equilibrium going to be 0.4911. Meanwhile, for the H plus and the methanoate ion, we're going to get 8.9 times 10 to the power of negative 3 respectively. Okay, but since the question only asks for the degree of dissociation, we can directly find it by comparing the concentration changes divided by the initial concentration. And we're going to focus only for the methanoic acid, which is HCOOH. So the change in the concentration is 8.9 times 10 to the power of negative 3. And then our initial concentration is 0.5. Okay. So once we do the maths here, we're going to get the alpha to be 0.0178 without any unit, because concentration unit and the other concentration unit is going to be cancelled out. So we don't have any unit for the degree of the dissociation. And we can know that the methanoic acid is a very, very weak acid because it only dissociates partially by itself. Alright, now we're going to look into the example number 2. So for the reaction of N2O4 gases, it's going to be converted into 2 mole of NO2 at a certain temperature, and it has a value of Kc to be 4.50. If 0.20 molar of N2O4 is introduced into the container at this temperature, we need to calculate the percentage of the dissociation of the N2O4. And in order to do this, we need to find the X value, which is the change in concentration. So in order to find the change in concentration, we need to use the ice table. So we have the equation of N2O4 gases converted into 2 mole of NO2 gas. So initially, we're going to have 0.20 molar of N2O4 inside the container. And the concentration of the product at the initial stage is 0. But as time goes by, the reactant will going to be reduced by an unknown amount of X. Meanwhile, the concentration of the product will be increased by 2x because it has the stoichiometry of 2. And at equilibrium, we're going to get the concentration of the reactant to be 0.2 minus x. Meanwhile, the concentration of the product to be 2x. Okay? And from here, you can write the Kc expression first because you know that your Kc is equal to 4.50. Okay? So you can write the Kc expression in order to find the value of x. So Kc is basically the concentration of the product, which is NO2 to the power of 2, divided by the concentration of the reactant, which is N2O4. So we're going to get 2x to the power of 2, because it refers to NO2. And then for the N2O4, we're going to substitute that into here. And then our Kc is equal to 4.5. So we're going to bring and expand the bracket here on the right hand side. And we're going to get to be something like this. And then we're going to bring all the terms here on the left hand side so that we can form a quadratic equation. Okay, similarly as what you have learned in the previous video. So we're going to get the equation to be something like this. And then we're going to solve the quadratic equation in order to find the value of x. So when you insert that inside your calculator, you're going to get two possible values, which is x is equal to 0.173 and x is equal to negative 1.30. And for this, we're going to select the more positive value because when we select the negative 1.30, when we substitute in here, we're going to get the negative concentration, which is illogical, tidak logic. So we're going to ignore that because it is illogical. Okay, so now we have find out the value of x here. And now we can find the percentage of the dissociation of N2O4. So the change in the concentration of N2O4 divided by the initial concentration. And then since we are talking about percentage, then we can multiply it by 100%. So the x here is equal to 0.173. And then our initial concentration is 0.20. And then times 100%, then we're going to get the percentage of dissociation going to be 86.5%. So this is how we're going to answer the question related to the degree of dissociation. Now we're going to look into the reaction quotient. So reaction quotient is calculated by substituting the initial concentration or pressure of the reactant and product into Kc or Kp expression. So let's say if we have a general equation of AA plus BB produces product CC and DD, which is at equilibrium, we're going to get our equilibrium constant to be something like this, similar as what we have learned in the previous videos. So A, the concentration of A, B, C, D is all referring to the concentration at equilibrium because we are talking about the equilibrium constant. However, for the reaction quotient, which is QC, it basically refers to the same thing. But differing the QC with KC is basically at the time point. Okay, the QC can be at any concentration. Usually, we gonna take it at the initial stage. So, QC dengan KC mempunyai expression yang sama. Cumanya, KC refers to equilibrium. Meanwhile, QC can be at any concentration at any point of the reaction. Alright, so now we're gonna learn on how to compare our Q with Kc. Okay, so by comparing that, we can determine whether our reaction is at equilibrium or not. So first, if we have our reaction quotient, the value of Q is lesser than K. Now, when the value of Q is lesser than K, then we know that the system is not at equilibrium. Okay, so when Q is lesser than K, it means that the denominator, which is this part here, is very, very large, and as a result, our Q here is low. Okay, and that is why Q is lesser than K. Okay, so it means that our concentration of our reactant is very, very large. And in order to reach equilibrium, we need to make sure that our Q is equal to K. Therefore, Q needs to increase so that we can equal the value. And as a result, we need to increase our product and our reactant must be decreasing. And as a result, our reaction must shift to the right. Okay? Sebab when the reaction shift to the right, we know that our concentration here will get higher, and as a result, our Q will get higher as well, and it will make Q is equal to K. Alright? And to make life easier, it's usually the reverse of the direction here. So when Q is lesser than K, then you automatically know that the reaction will shift to the right because it's always the reverse direction of the arrow here. Okay? Now we're going to look into Q that is greater than K. So when Q is greater than K, then the system is also not at equilibrium. Okay, let's say if you have an equation here, when Q is very, very large, it means that our concentration of C and our concentration of D is very, very high as well. Okay, which is the product. So when the product is very, very high, we need to reduce back the product so that our Q can be reduced. So in order to reach equilibrium, we need to ensure that our Q is equal to K, and therefore Q needs to decrease in order that Q is equal to K. So the product must be decreased and the reactant must be increased. So the direction of equilibrium will shift to the left. Okay, so when it shifts to the left, our concentration here, our product will be changed back into the reactant and it will lower down. And as a result, our Q will be lowered down as well. And this will make Q is equal to K. And that is why the reaction will proceed from right to left in order to form more reactant until the equilibrium is reached. Now, let's say if you have Q is equal to K. So when Q is equal to K, then we know that the system is at equilibrium. So when Q is equal to K, we can say that the concentration or the pressure of the reactant and product has attained their equilibrium values. So the forward reaction in order to produce a product and the reverse reaction is basically equal for both forwards and reverse direction. And we can know that the equilibrium is reached and there is no net reaction that is gonna occur. And here is the summary of what you have looked just now. So when Q is lesser than K, then you know that the reaction will go in the reverse direction, in which it needs to go from the reactant into product. So it's going to shift to the right. Okay, and conceptually, when you know that your Q is lesser, it means that your reactant going to be very, very high. Okay, so that is why we need to reduce back so that the reactant can be reduced, and we need to go to the right so that our product gonna get higher, and so that this value here gonna get higher, and then our Q gonna be higher as well, and hence will make Q is equal to K again. Alright, so similarly for this part here. So when Q is greater than K, then it needs to go to the reverse direction. Alright. Now we're going to do example number 1. So the reaction of N2O4 gases produces 2 mole of NO2. And then we got the Kc, which is 0.21 at 100 degrees Celsius. So at a point during the reaction, the concentration of N2O4 is equal to 0.12 molar, and then the concentration of NO2 is 0.55 molar. Is the reaction at equilibrium? If not, in which direction is it progressing? Okay, so it says here that at a point, so it can be at any point. So the concentration here is at certain point. So what we can do here is we need to find the value of QC. Okay, so when we find the value of QC, we can compare that with our KC. Okay, so by comparing that, we're gonna know whether the direction is at equilibrium or not. So if not, we need to determine the direction. So we're gonna write the equation once again, and then we're gonna write the QC expression in which it's equal to NO2 to the power of 2 divided by the concentration of the reactant, which is N2O4. And then our NO2 here is referred to 0.55 to the power of 2 divided by the concentration of the reactant, which is 0.12. So once we do the math, we're going to get our QC to be 2.52. So as what you can see here, our QC is 2.52, but our KC is 0.21. So we know that our QC is greater than KC. Hence, we know that the system is not at equilibrium. Okay, so bila QC terlalu tinggi, then we know that our product is very, very high. And as a result, we need to shift to the left so that our QC can be reduced back when our product is decreasing. Okay, so we can say that the reaction will proceed to the left until QC is equal to KC in order for it to reach equilibrium. Alright, now we're going to look into example number 2. So for example number 2, the Kc for the formation of the nitrosyl chloride, which is an orange-yellow compound from the nitric acid, from the nitric oxide and the molecular chlorine is 6.5 times 10 to the power of 4. So here is the Kc and here is the equation. And in an experiment, 2 times 10 to the power of negative 2 mole of NO, 8.3 times 10 to the power of negative 3 mole of chlorine, and 6.8 mole of NOCl are mixed in a 2-liter flask. So we know that we have our concentration by dividing mole with the volume. Okay, and we need to determine in which direction will the system proceed to reach the equilibrium. So we need to find the value of QC, and then we need to compare that with our KC, which is given as here. Okay, so we know that this is our equation as well as our Kc. And then in order to find the initial concentration, we can divide our number of mole with the volume. So for the concentration of NOCl, it's going to be 6.8 divided by 2. We're going to get the concentration to be 3.4 molar. And then for the concentration of the NO, it's going to be 2.0 times 10 to the power of negative 2 divided by the volume of the flask, which is 2. We're going to get 0.01 molar. And then for the concentration of the Cl2, it's going to be 8.3 times 10 to the power of negative 3 divided by the volume of the flask. So we're going to get the concentration of the Cl2 to be 0.0042 molar. So we already got the initial concentration. And by finding the initial concentration, we can now find the QC, and we're going to do that in the next slide. So here is the initial concentration. And then for the QC, we're going to write the expression once again, which is our NOCl2 to the power of 2. And then divided by the concentration of the reactant, which is NO to the power of 2. And the concentration of the Cl. So we're going to substitute the value into the expression here, which is the NOCl, which is 3.4 to the power of 2. NO going to be 0.01 square, so do not forget that. And then our Cl going to be 0.042. So once we do the maths, we're going to get the QC to be 2.75 times 10 to the power of 7. So now we can compare our QC with our KC. So our QC is definitely larger than our KC. So we can say that QC is greater than our KC. So when QC is large, then we will know that the concentration of our product is very, very high. So in order to reduce back, we need to go to the left hand side so that our concentration of the reactant going to be higher. Okay, so the system is not at equilibrium, and therefore the concentration of the product going to be very large. So we're going to reduce it back so that our Q can be reduced, and hence it's going to be Q equal to K until it reaches equilibrium. Okay, so you're going to say that the reaction will proceed to the left until QC equal to KC. Alright, so I think that's all for today's video. See you again some other time. Bye!